So today we're going to have a look about this idea of set notation, set and terminology that goes along with that. Briefly mentioned the word set yesterday when we talked about a sample space. A sample space is an example, I guess, of a set. It's basically a collection of objects. Now in sets we call them elements rather than objects, but yeah. So the language associated with it. We can have what's called a listing set. And that's simply where we list every object in the set. So the set A there is simply the numbers 1, 3 and 5. Okay? Or we could have a describing set. So instead of writing all the elements down, because, okay, 1, 3, 5 was only 3 numbers, that was easy. But if you've got a very large set, it might be easier just to describe all the elements of the set. So this particular one, I would describe as, oh, well, it's the first 3 odd numbers. We're talking about the first 3 odd numbers. Equal sets, 2 sets that contain exactly the same elements. All I've done is written them in a different order there. So set B, 5, 3, 1, would be equal to the set A. They have the same elements. Empty set is the set that has no elements. You sometimes see the word null instead of empty. So the null set, same thing. It's the empty set. As opposed to the universal set, which has every possible element. So that, I guess, would be like our sample space in probability. It contains every possible outcome. And then a subset is just a set within another set. So C would be a subset of both A and B. C, the set C, they just contain simply the number 5. And so it's contained within both A and B. Well, intersection, hopefully we're familiar with that one, but that's the objects they have in common. So if I create another set here, D, 2, 3, 4, then the intersection of A and B is 3. They're the numbers that are in both sets. Okay, as opposed to union. Union then is all of the objects in all of the sets that you're talking about. So if I was just now talking about A and D instead of the intersection, talking about the union, it would now become 1, 2, 3, 4, 5. So it's all the objects in both of the sets. Complement. Again, similar to the terminology we saw in probability when we talked about the complementary event. It was the when it didn't happen. So same sort of idea. They're the ones in the universal set that are not in the set. So the universal set has all of the elements. You have, say, set A, which I've got there. Well, its complement, if we said the universal set, all we were interested in was the first 6 integers, then the complement of A would be 2, 4, 6. Because remember, set A were the odd numbers. So its complement would be the even. All right, so some notation that we use when we're talking about sets. Okay, the 0 with a strike through it, that's the symbol for null. Remember we said null is also the empty set, so the other way we could do it is simply put the braces, but then there's nothing in it. So that would also represent the empty set. Is an element of, so it belongs to the set. So 3 is an element of A. 3 belongs to the set A. The absolute value symbol, again we talked about that yesterday when we were talking about probability. Absolute value just means magnitude or size, so the number of elements in a set. Another way they sometimes notate it is n, and then in parentheses whatever set we're talking about. Subset, I guess best way of describing it is a sideways U, I guess. But so C is a subset of A, C was also a subset of B. B is a subset of A, but you'll notice there's a line underneath. Because remember we said B was also equal to A. So it's both a subset, but they're also equal sets. And then the null set is a subset of A. In fact, the null set is a subset of every set because it's nothing. So everything has that nothing in it. It's really weird when you think about it. You think, well, hang on, it's got objects in it. Yes, but if I was to take away those objects, I'd be left with nothing. So therefore, nothing must be in the set. So the null set becomes a subset of it. Intersection is the upside down U. So we said that before. The A intersection D was 3, whereas C and D had no points in common. So it's the empty set union the U. Complement, again, like we saw yesterday in probability, the bar over the top means complement. In set notation, we also see this other one. Sometimes they put A dash to mean the complement, or with a C. I suppose that one makes sense, C for complement. But I mean, the most common one is the bar on top, because we see that in probability as well. One of the key things about set notation that makes it really useful are these Venn diagrams. Certainly useful for probability as well. It's another way of representing sample spaces, and you can see what things have in common and so on. So it's more a visual or a geometrical way of representing the sets. So the universal set we usually represent with a rectangle. Okay. So here's an example one. So the blue rectangle, I guess, is saying, well, this is everything we're considering. And back to those first 6 integers we were talking about. So that's in the universal set. And then the sets themselves, I've just used circles for, and how they would be located. So remember, set C was just 5. So it was a subset of B, which is 1, 3, 5. But hang on, A also contains 1, 3, 5. So B and A are actually the same set. D was 2, 3, 4. So there's the intersection of the 2 is 3. And so on. So that's our Venn diagrams. So the sorts of things we could see, well, if C is a subset of B, so that's what I was saying there before, well, the set C was the number 5, it's totally within the set B, which I've just shaded grey there to make it a little bit more, well, obvious if it wasn't obvious anyway. So intersection, that's what they have in common. That would represent union, so it's all of the objects. And, hang on. That's so good, I put it again. Why did I do that twice? I have no idea why I put that twice. Okay, and then disjoint sets, they're the ones that yesterday I was talking about in probability we called mutually exclusive. They have nothing in common, it can't happen at the same time. So C and D would be mutually exclusive sets. Okay, so how can we use these Venn diagrams to help us with counting how many objects are in sample spaces and things like that? So, all right, here's a basic rule. The number of objects or elements that would be in A union B would be the number of objects in A plus the number of objects in B, but you would take away the number that is in the intersection, because you would be double counting those because they're in both A and B, so you need to take away the intersection. It's actually very similar to a rule you might remember from probability. It's basically the same thing. So okay, we've got a class of school, and many of them are on the swim team. There are 18 students in this class, 7 swim freestyle, 4 swim backstroke, and 2 do both of the strokes. Okay. So find the probability that a random student selected is not on the swimming team. So this is just another way, as I say, of drawing up a sample space to help you with a probability question. So the universal set there, the rectangle, would be all of the students. And then I've just called the set F for freestyle, the set B for backstroke. So we try and create, based on the information we've got. Well, I know there's 2 in the intersection, because they said 2 swim both strokes. 7 swim freestyle, which means there must be 5 in the other set. Or not in the other set, but not in the intersection, I should say. And backstroke, they said 4, so there must be 2. But they said all up, in the universal set, there's 18. Now I've only accounted for, what's that, 9 all up. So there must be another 9. So we do a calculation. Using that formula before, we can say, oh, well, F union B, we know is 9. So therefore, there was 18 all up, 9 not in the swimming team. Do you actually write that down? As I say, but you probably just do it in your head by filling in the diagram as you go. But now you can read from that the probability. We know there's 18 all up. Probability, random student is not on the swim team. The 9 not in the swimming team, so 9 out of 18. Probability of a half. All right, so as I say, it's just another way of drawing up your sample space to help with probability questions. So we'll have a go at 12 C and D, see how we